Hi, welcome to another edition of Easy Theory. So let's continue our lecture series on algorithms. And by continue, I mean let's actually look at a real algorithm that we actually all care about, which is let's multiply numbers together. So let's try to multiply x times y, and let's be sure what x and y are. X and y are both integers. Let's just say positive to make things easy. If I could spell positive. So the algorithm that in certain terms that you were taught a long time ago in grade school probably was about using the method of multiply one digit of y times x, and then the next digit of y you shift it over by 1. So just like as an example, let's do 15 times 22. Then the grade school method said, let's look at this digit right here, this last 2, and then multiply it by 15. So that gives us 30. And then you look at this this first 2, it doesn't have to be exactly 2, the same as this other 2, but it just happens to be 2 in this case. Then what you do is you multiply this 2 by 15 again, but you're going to shift it over one place. So you're going to put a 0 down and then put the result, which happens to be 30 here. So then if you then add these two numbers up, then you'll get 330. And we can verify that this is actually right. So this actually works, but what we want to do is to write this as simply as possible. Well, if you try to do this, so let's just say x is x1, x2 up to xn, and y is y1 up to yn, then what we could do, although I'm not going to do it here, is we can do a double for loop on these, kind of like how we did this. So, or maybe just a single loop. It depends on how you implement it, but what we can do is say, okay, we're going to take yn right here, multiply it by this whole thing, and then we'll go to yn minus 1, multiply by this thing and shift it over one place, and then etc. all the way down. But here's the problem. We're going to have all these numbers still to add, first of all, and so therefore we need to maintain all of these numbers in some structure, which you could do, but it's quite cumbersome to do. But the more important problem is I said multiply this digit by this whole number, but that's just a simpler version of the same problem that we're trying to solve in the first place. So that's kind of annoying. So what could we actually do here? So let's try to make this a little simpler without having to worry about like the number of digits in these or like maintaining all of these numbers to add at the end. Let's try to make this even simpler. So we're going to use a technique called recursion. And in a nutshell, all it means is solve a simpler version of the same problem. But then you say, oh, Ryan, isn't that the same problem that you had before? Like, you had this one digit times this number and you couldn't do that. The thing that we're going to actually do to work with this, that makes this work and this not work, is that we're going to make the problems simpler and simpler and simpler until we get to what is called a base case. So what we're going to do is we're going to have a complex problem that we need to solve. Although this one isn't that complex, but it generalizes well. And then what we're going to do is we're going to simplify in some way over and over and over until we get to a base case, which is a really simple version of the problem that doesn't require any intuition whatsoever. So in our case, for multiplication, this base case will be multiplying by 0. So if you multiply any number by 0, you're going to get 0. And so you don't need to know anything about multiplication to do that, other than if you multiply something by 0, you get 0. So let's actually try to think about, what does x times y even mean? Well, if x or y is 0, then clearly the result's going to be 0. So let's actually work with this in this way. So it's going to be 0 if x is equal to 0, obviously, and it's 0 if y is 0. But let's assume that y is not 0 for now, because if y is 0, then the result's 0 anyway. So let's assume y is not 0, and we're going to vary what x could be. Okay, well, let's see. Well, if we think about what we're really doing up here, what we're really doing is we're working in base 10. And so when we're multiplying by the bigger, the tens digit, for example, we're going to shift over everything one digit. But everything we do in computing is in binary. It doesn't really matter which one you use, but let's just assume that this is in binary. So we're going to assume that these two numbers are in binary. And you can generalize this to base 10 and other bases if you wanted to, but let's just stick to binary because it's easy. Well, what we're really doing, if we multiply them in binary, is we would shift the number over by one position, which is corresponding to multiplying it by 2. So if we think about it a different way, what is a simpler version of the same problem? Well, if I divide x by 2 and multiply it by y, that's a simpler version of the same problem. And then what I do is I just multiply the result by 2. So if I divide x by 2 and multiply it by y, and then multiply it again by 2, then I get x times y. So you may think, okay, well that's trivial. X over 2, so half of x times y times 2 is going to be x times y. It doesn't really help you. The thing is, we can actually do the times 2 part really easily, and we can pass control to a simpler version of the problem and at the end multiply it by 2. So what we're going to do here is we're going to do x divided by 2 times y plus y. And I'm actually intentionally writing it this way so that we can see that we're only working with a y, one instance of y, and then multiplying it by 2. The problem is, what if x is not divisible by 2? Well, it either is or it isn't. So what would we need to do? Well, if x is divisible by 2, we don't need to do anything. So if x divisible by 2, in other words, that it's even. That's another way to say it's even. But suppose that it's not divisible by 2. Well, if it turns out if we do this, and I divide by 2 and it's not divisible by 2, a way to fix it is to use the so-called floor function. Then multiply by the y plus y thing, and then add another y on top of it. So, and I invite you to actually check this for yourself, that this really does work. So this is called the floor function. And what it does is rounds down to nearest integer. Okay, so we could have actually done it here too, but it just muddies up the picture. So the key difference is, I should say otherwise here. Okay, so what we're doing here is if x is not divisible by 2, then we round down, multiply by 2y, and then the remainder, so to speak, is this plus y at the end. So notice, so you may think, okay, why are we really doing this? Notice that the y is exactly the same in every place. So what we can do is when we're given x and y, we have those values of x and y, and then we can reuse them over here. So how are we going to actually do that? So I'm going to make a function called multiply x and y. So the way that we usually structure these recursion things is first we're going to put the base case. So the base case here is that x is equal to 0. So as step 1, if x is equal to 0, then we return 0. Because clearly x, which is 0, times y is 0, obviously. But otherwise, we need to check if x is divisible by 2. Well, actually, we can combine the two steps in this way. So let's actually do it this way. So what I'm going to do is I'm going to do that floor function. And I mentioned before that we could put the floor function here too, because if x is even and I divide by 2, it already is an integer. So if I round down, it's the same number. It doesn't change anything. So I might as well just do that anyway. So I'm going to have x prime. I'm going to set that equal to x over 2 floor. Okay? And so what am I going to do here? Well, notice that you don't actually need to combine it in the way that we're doing, but it makes things easier. Notice that the y plus y bit is used in both of the recursive cases. So these are the recursive cases. This is the base case, recursive case, recursive case. So how do we actually do this? Well, we know that y plus y is used in the solution, in the recursive case both times. So I'm going to set y prime to be y divided by 2, not divided by 2, times 2, so 2y. And what I'm going to do here is I'm going to appeal to the function to make sure that x prime times y prime works, that it's computed correctly. So what I'm going to do is I'm going to call the product p, and I'm going to recall the exact same function, multiply with x prime and y prime. Okay, why does this work? Well, I mean, there's more stuff after this, but why is this a good idea? You may think, well, if you're calling this function inside of itself, isn't this just going to go circling over and over and over like this? Here's the beauty in how we design this. Notice that x prime is smaller than x, always. Is always smaller. So x prime is going down, 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 down. Then at some point, because it's a positive integer, it's going to hit 0 eventually, which means we eventually hit this step. And so we are not going to go through this infinitely many times. Okay, y prime is growing, but x prime is shrinking. And then, so now what we do is we figure out, okay, so this is the product that supposedly works, but we had that difference if x is odd. And then if x is odd, we need to add y onto the result. So what I'm going to do here is if x is odd, not x prime, but x itself is odd, then what I'm going to do is I'm going to add onto the product that we've determined so far, y, not y prime. And then all that we need to do at the end is return p. Okay, so what we're doing here is we're changing the structure of the multiplication, and so the result of this multiply should be the same other than when x is odd, but assuming that x is even, the product is exactly the same, but we're rephrasing it in a different way here. So, so x prime is smaller, y prime is bigger, and then as these two variables change, the product stays exactly the same other than when x is odd. And then eventually x hits 0, which we know how to solve that. So then we're assuming that this multiply works, that it gives us the right result. And then when we get control of this function, the value returned here, we only need to make this small adjustment if needed. And then whoever called multiply to get it to our level, they're going to need to make this change if needed, and then it's going to work its way back up the tree until we hit the top. So let's actually visualize this in practice. So let's try to compute multiply. I'm going to make these numbers up. So let's do 5 and 7. So that obviously should be 35, but let's just make sure that it works. So we come into this function right here. Is x equal to 0? No, it's not. So we come down here. So I'm going to set x prime to be the floor of 5 over 2, which is 2 here. And then, then y prime is going to be 2 times y, so y is 7 here. So it's going to be 14. So notice, 2 times 14 is not 35. So the product is not right if x is odd. But that's why we have this adjustment on the end to add 7 back onto the result. Okay? So now what we're going to do is we're going to call multiply of 2 and 14. So what is that going to do? Well, is x equal to 0? No, it's not. So we're going to do another x prime. So each of these functions has their own copy of x prime and y prime. So x prime is going to be 2 divided by 2, which is 1. Y prime is going to be 28. So we're going to call, I'm going to shorten it to be mult in this case. So 1 along with 28. So x is not 0 here. So we're going to have x prime to be 1 divided by 2 floor, which is going to be 0. So the next time is going to give us 0. We call mult. So then y prime is going to be 56, I think. So then we're going to call a mult of 0 and 56. So then now that's going to give us, so this is going to return 0 pretty obviously because of this return at the top of the mult function. So what are we going to do here? So now here's where we need to be absolutely sure we know what we're doing. So this mult is going to give us, so that's going to give us 0 obviously. So now what are we going to do about 1 and 28? So we notice that 1 right here is odd. So if x is odd, which it is in this case, we're going to add 28 onto the result that we got, which is 0 here. So p is going to be 0, which is what it was before, plus 28. So therefore, we're going to return 28. Oops. We're going to return 28. Okay? Which is what we should get. 1 times 28 is 28. So now let's come back up to this function right here. So the result of calling mult 1 and 28 is 28. We realize that this particular x that we're given was not odd, it's even. So we don't add y onto the result, which means that we're going to again return 28. And then come back up here. This is going to give us 28 yet again. But we realize that 5 is odd, so we're going to add 7 back onto this result. Okay? So that's a short introduction into recursion, and we're going to actually see quite a few more examples in the upcoming set of videos. The idea being that we break a problem up into smaller pieces, where in the smaller pieces, we assume that we know what that the answer, assume that the function is correct on the smaller versions of the problem until you reach the base case where the recursive calls, which are the smaller versions of the same problem, eventually are going to hit. So in this case, we're eventually going to hit x equals 0. If the number x was negative, we may not necessarily get 0. But because it's positive, we know that dividing by 2 and rounding down eventually will get a smaller and smaller number. For example, if it hits 1, and then when you get to 1, you divide by 2, which means that you will hit 0. Okay? So hopefully that was interesting. If you have any other ideas about recursive algorithms, put them in the comments below. And as always, I'll see you next time.